So we're going to begin our final chapter of Chem 222 here, and this is a chapter that's all about chemical equilibrium, which is a very important and key idea for 223. So this is really a lead into 223 in this chapter. And we'll talk more about it near the end, and I'll have a little worksheet I made last time I taught this class, or a little, I don't know about worksheet, but a little paper or something like that helps you kind of understand how it's going to lead in, because there might be a bit of a gap between when you take 223 and now, so feel free to hang on to that to help kind of refresh your memory about what we do at the end here, and it will kind of tip the handle a little bit about what's at the beginning of 223. Okay, so let's start out here, and what is chemical equilibrium? So this is what I call one of the crown jewels of chemistry. This is such a fundamental key idea, so important to chemistry, and we're finally going to talk about it. So this chapter is a bit of a wild ride. It's going to lean a lot on reaction rate stuff from the last chapter with a new twist. So understanding reaction rates really helps understand chemical equilibrium, especially at the beginning when I talk about what it is. So feel free to kind of flash back and look through that stuff at the beginning here. But the new trick is that our reactions are now reversible. Now, not every reaction is reversible. So there's a reason I said if a reaction is reversible. And so what that means is we've always talked about stuff going left to right. We've got our reactants, we've got our products. We start with something, we make something else with it. But it turns out that spontaneously, a lot of these reactions, again, not all of them, but this isn't very uncommon by any means, can reform the reactants. So we call this our forward reaction. So everything you saw from the beginning of 221 until now was a forward reaction. But now we can reverse those reactions. So this is an example of a reversible reaction. It can occur in the forward direction, but two HIs can collide and reform H2 and I2 gas. So this is something that is reversible. And so, if our products are reforming reactants, that's our reverse reaction. Now, we don't want to write everything twice. Chemists, we try to avoid doing work as much as possible. It's one of our signature, professional skills. So what we do, we use this little arrow right here. It's kind of a half arrow going to left to right. So forward, half arrow going right to left, reverse. This means it's a reversible process. It's an equilibrium process. And so instead of writing two reactions, I can write one and put all that information in it. Half the writing, twice as good, right? So if a reaction is reversible, both the forward and reverse reactions are going to be occurring. And so we denote that. How do you know if a reaction is reversible or not? I'll tell you. We'll talk about how you can tell if it's more likely or less likely, but in general, you don't really know unless you measure it. So I'm telling you right now, this is a reversible reaction, so this is how we denote it. And if you ever see this, that is a reversible reaction. So something like a combustion reaction is not reversible. The flames don't spontaneously pull back in and all the CO2 in the atmosphere turns back into, wood or propane or whatever you're lighting on fire. So that's, that's a one-way ticket that has a forward direction only. And if you take the really long-term view and you're like, oh, but then the trees, they take the CO2 and they make wood, and then we dry the wood out and we light it on fire. Okay, you can make an argument it's reversible, but that's quite the process. In general, it's like it's happening in my beaker. So this is something that would happen in a container. We could see it, and you can actually manipulate which side is favored. We talk about that near the end of the chapter with Le Chatelier's principle. So this is an equilibrium process, for sure, under any definition. All right, now, I have only explained reversible reactions. I have not yet explained what equilibrium is. I want to be clear about that. Because when we're at equilibrium, that means that our forward and reverse reactions have equalized out. And so if we put H2 and I2 together, we start making HI, and eventually we stop making more HI, but we haven't used up all of our H2 and I2. And so we get a situation where all of our concentrations have stopped changing over time. And so that is when we're at equilibrium. When it settles into a sweet spot, that's equilibrium. And this is where it starts getting a little tricky. Because you see this and you might think, oh, all the rates are zero. Well, If you zoom out, yes. But what you really have is that the reactions are still happening. So equilibrium is a dynamic process. It is constantly having motion and change. You know, if I am a specific hydrogen in an H2, and I'm in an equilibrium system where we've reached equilibrium, I might be on an HI for a little bit, I might come back to an H2, but overall, the total population of HIs and H2s isn't changing. It's just changing which one I'm on at any given moment. So we're still making HI, but we're also making H2, and we're doing it at a rate where they cancel each other out. So we're not observing a net change of how many HIs or H2s or I2s. All of our species are a constant concentration, but this is because, and this is where the last chapter stuff comes in, our forward reaction is happening with a certain rate, but the reverse reaction is occurring at the exact same rate. So the best definition for equilibrium, the concentration one is correct, but really the best definition is that it's when the reaction rate for the forward reaction and the reaction rate for the reverse reaction equal each other. That's when you're at equilibrium. And that's what causes the concentrations to stop changing. So all of our changes in concentration cancel out because, yeah, I use up some H2, but there's a reverse reaction that occurs that makes some more just as fast as I used it. That's equilibrium. So there is, you know, chemical change happening, chemical reactions occurring, but no net changes. When I look at the whole picture, nothing is changing in the big picture. So we're going to draw a little kind of reaction rate diagram here in a second. I got to clear the board. We're going to show how equilibrium is self-determining. It finds itself automatically. If I want to know what a system is in equilibrium, all I got to do is leave it alone for a little bit, come back and measure it. That's it. All right, so we make some space. We're going to talk about that. All right, so here's a little graph. You know, this is rate versus time. And we've got our forward reaction rate, we got our reverse reaction rate. And what happens is, this is a situation where we've loaded up, essentially we put together a reactants only. There were no products to start out. And what happens is our rate starts to drop. We talked about this in the last chapter. Reaction rate declines over time because we use up our reactants and their concentration drops. And as the concentration of reactants drops, well, the rate drops. But guess what happens in the reverse reaction? We start out with nothing. We don't have a rate, right? But as we start forming products, well, we start getting what we need to do the reverse reaction. And so as the concentration of products increases, so does the, and again, products being things on the right-hand side, so like HI. It gets a little squirrely, I know, but just hang in there. So, you know, the products of our forward reaction become the reactants of our reverse reaction. Fun with words, right? But as that concentration increases of, say, like HI, then our reverse rate is going to increase. We have more HIs that collide into each other and reform H2s and I2s. And guess what happens? We have one rate that's going down, we have one rate that's going up. They're going to meet. And when they meet, we're at equilibrium. The reaction rates have found each other. And this happens automatically. I don't have to do anything as a chemist. This is just nature grabbing the wheel, right? Taking care of business. So, it is a dynamic process. So these reaction rates are still not zero, all right? This is not zero right here. You know, zero would be all the way down here. So the reactions are still occurring, but they cancel each other out because my forward reaction is going just as fast as my reverse reaction. I'm making HI just as fast as I'm breaking HI. That's what's going on. Now, you might think, well, what if, you know, instead of loading up with all reactants, what if we just started with only products? Same thing is going to happen. We just flip it. Then this would be, you know, what was above and below would switch. We'd have a reverse on top and our forward on the bottom. Because our products would break down and form reactants, which would create the forward reaction and they'd equalize out. So equilibrium always occurs if the reaction is reversible. It is self-finding, and it is because of those properties of reaction rate that we talked about. And so this video, it'll probably be like 10 minutes or so, but it is such a key fundamental discussion of what equilibrium is. And before you move on, you should really make sure you understand what I'm saying here. So that, you know, equilibrium is, it's good, you know, if you have a reversible reaction, equilibrium happens. We don't make it happen, it just happens. And I just explained why using reaction rates as an argument. So I'm leaning on the last chapter, which was a very technical chapter as well. But we're going to build on it. So make sure this is making sense, because if you can get this kind of fundamental stuff down, it'll really help you build intuition later in the chapter when the math starts really coming into play and things get a little bit more squirrely. So I really encourage you, make sure this one makes sense before you move on. All right. So we're going to start talking about kind of the mathematical properties next. Very beginning of that. We're going to talk about the equilibrium constant. But before we do, make sure, like I said, this fundamental stuff is really sinking in. It's so important.